All right, guys, welcome to Pre-Calculus 122. We're talking about inverses today. So you've likely seen these in the past. We're going to kind of go over them a little bit more in depth today. So to start off, we have a little bit of a problem. Sean is a factory manager. She knows that on any given day, N employees can fill P number of orders, and P is going to be equal to 2 times N raised to the second power minus 8. So given that information, what I want you guys to do is go ahead and pause the video, work through A through F once you are done, or if you get stuck, then go ahead and resume the video. Okay, so going through this, if we do the first few, it's relatively easy for us to kind of figure out how many orders we're going to need. First they want the domain. In context, our number of employees is going to be 0 or greater. You could also say it's 1 or greater because you really don't care about it being 0. But then for part B, how many orders can 10 employees fill in a day? Well, if I plug in 10 in as 10, then I get 10 to the second power, which is 100, times 2, which is 200, minus 8 is 192. Right, so we can kind of do that. Then we get to like C. Well, if we have 120 orders to fill, then how many employees do we need? And so to do that, as well as part D, where we have 64, we plug in that number into P, and then we do a little bit of algebra, get N by itself. Now you're going to be taking a square root of both sides on those ones. In doing that, you're going to have a plus or minus. Now we really don't care about the negative option because we're not going to have a negative number of employees doing work for us. So we only really care about that positive option. But then the real meat of this comes to part E. So as you probably saw in part C and D, you do the exact same mathematical steps both times, just with a different number in for P. So the kind of shortcut here is, well, we could actually take this equation and we could solve it for N as opposed to being solved for P. So when we do that, pull up my docking camera, we actually end up having P equals 2N squared minus 8. And we're going to add 8, so we have P plus 8 equals 2N squared. Divide by 2, P plus 8 over 2 equals N squared. And then we need to square root both sides. So we get plus or minus big square root of P plus 8 over 2 equals N. Now, I can kind of change this around a little bit. Since I said that my domain is only positive because I don't really care about negative numbers of employees, I really don't need the plus or minus. You're going to see me do that most of the time because if you get in the habit of just not using it, then you're going to forget it when you actually do need it. So that's why I kind of recommend still doing it. I would rather see you put it there and then not really need the like negatives than you just forget it, and then when you do need it in the future, you forget about it then. So that's kind of my rationale there. So then we have this equation. So now we can just plug in whatever number of products we need in this equation here, and we get the number of employees which we need out of it. Awesome. So that's our little shortcut which we kind of built there. Now what that is really the inverse, as we're going to find. So we're going to go ahead and graph this, as well as graphing the original problem here. So if I pull up my Desmos, my original graph is 2x to the second minus 8. Again, Desmos likes x's, not other variables when you're trying to graph. And then I want the square root of x minus plus 8 over, I put that in parentheses, over 2. And then we get that. So they look fairly similar there. The thing that's kind of missing is on the red graph, I really only want a domain that is larger than 0, right? And in truth, I probably only want it when it is larger than 2, because if I have 1 employee, then I can actually make a negative number of products, which is not really going to be feasible for me. So I really, so you could say that for your domain, but the main thing that I want you guys to see here is the shapes of these graphs. Now, we only really want the right-hand side of this red graph. So if I were to erase this left-hand side, how would that right-hand side and this blue graph look? Right? It might also help if I actually show the negative side. So I'm just going to copy that, make it negative, and I'm going to change the color to being blue so we're looking pretty. So you can kind of see that relationship here a lot better. We only removed that negative side because it wasn't in our domain there. But you can see that really these are the same graph, but they're kind of turned, right? They're actually reflected over the line y equals x, right? So if I were to take the red graph and fold it over the purple line, I would get the blue graph and vice versa. So that's what kind of happens when you just change what you're solving for there. So again, those are called inverses. You've seen those in the past. It shouldn't be things that are brand new to you. All right, so let's hop back over here. All right, so next problem here, number 77. We're going to give you a resource page. I'm just going to pull it up here so that you guys can see it. We're going to try and fill out the top part of this form. Let me pull this out over here. Let's make it bigger so we can do it nicer for us. There we go. Okay, so what I want you guys to do is go ahead and pause the video here and then try and fill out, hey, what would the inverse equation be? And then fill out this table. This first table is the table of the A original, and then it's going to be the table of the inverse. And then go ahead and graph the A original and graph the E-inverse. If you want to use Desmos to help you get an idea of that like graph, it's fine, or just use the table to help you graph. That's kind of what it's intended for. So go ahead and pause, go ahead and do that for me. All right, now that you're back, when we get the inverse here, I'm going to go ahead and pop back over. Let me pull this over here and then change this to Desmos. Not Desmos, I want my document camera. There we go. Okay, so my original equation was y equals x minus 2 cubed plus 5, right? So if I want to find the inverse of that, I basically kind of want to change around what I'm solving for, right? I can move the 5 over and then cubed root, and then eventually I'm going to want to transpose the x and the y, meaning you're going to take the x and the y's and switch them. Right? You can do that at the very end. I will typically do it first because otherwise I will forget to do it, and we're more used to getting y by itself than getting x by itself. So I'm going to say x equals y minus 2 to the third plus 5. And actually at this point, this is the inverse equation, right? I could just type this into Desmos and we'll graph the inverse right now. The thing we don't like about this form is it's not really a form we are used to using because we are used to having y by itself. That's kind of our default preferred form for any kind of graphing problem. So I still want you to get in the habit of getting into that form where that's kind of where we are going to want them 99% of the time. So we'll subtract 5, so x minus 5 equals y minus 2 cubed, and then we're going to cube root. X minus 5 equals y minus 2, and then I want to add that 2 over. Cubed root of x minus 5 plus 2 equals y. So there's going to be my equation for the inverse, right? And then when we get to the table, right, we can just take that table, plug in a value for, I believe they have started what, at -4. So a -4 in here, a -4 minus 2 is a -6. -6 times -6 is 36. -36 times 6 is going to be 180, 204, right? Just double checking my 216. Yeah, I forgot to multiply that extra 4. Okay, so you get 216 and then plus 5, sorry, a negative 216, and then plus 5 is going to be negative 211, right? And then you can kind of fill that out for the entirety of that table. Now, once you have that, so we're going to have our x and our y. For speed's sake, I'm just going to fill in some false numbers here. right? So if this is my original, when I want to get over to my inverse, all I really need to do is transpose my x and my y. So this was -1, 3, now it's 3, -1. This was 0, 7, now it's 7, 0. This was 1, 9, now it's 9, 1. This was 2, 12, now it's 12, 2, right? So we're just kind of transposing those things in order to get from our A original to our inverse. So I'm not going to go through every single one of those just because, for the sake of time, since you just did it. But when we go and then graph these, I will show you the graphs. Let me just change over to my Desmos. Okay. So our original graph is going to be x minus 2 to the third power, and then plus 5. And then on the bottom here, we're going to have our cubed root, which I believe, functions, miscellaneous. Where is the square? I'll just cheat. I'll show you a trick for doing those ones. X minus 5, and then I'm going to raise that whole thing to the 1/3 power, as opposed to trying to do a cube root, which is probably in there somewhere. I just don't want to dig through and find it. I think I just saw it as I closed that. So sorry about that. Plus 2. There we go. So there's the graphs. So the black one is the A original, the red one is the inverse. And we're seeing that same kind of mirroring over that purple line.
Attention freshmen.
Sorry about that. They promised me they would make no more A announcements, but they lied. So yay. Okay. So so we got that as our graphs. We have our A original, and then we have our inverse there. So again, the main thing that I want you to get from these graphs is how they look in relationship to that y is equal to x graph. All right, let's hop back over here. All right. And then this function invertible. Yeah, I didn't answer that question there. So you're going to see this term invertible quite a bit. Now it's really easy to see. Oops, sorry. It's really easy to see what if it's invertible by looking at the graphs, right? Invertible means that once you take its inverse is a function, right? So graphically, my black line is a function because it's our A original, and we kind of know that this is in function form. Now this other one. Does this red line pass the vertical line test? Well, yeah, you might say, well, there it looks kind of weird, but it gets really close to being vertical, but it never gets entirely vertical. So this does pass the vertical line test, so it is a function. Now, the last one we did earlier, where we had those parabolas, the vertical parabola, and then the horizontal one, that horizontal one was not invertible because the inverse is not a function. That's all the term invertible means. It means, hey, is the inverse also a function? Which, when you graph it, is super easy to see. All right, so now let's head back over to this. And we'll head down to this next one. All right, so we're back to this sheet, and this is probably one of the most ridiculous things we do the entire year. But they literally, the story is, someone spilt chocolate milk on the paper, and so now they can't see what the A original or the inverse was. Oh no, right? But they still have a table and they have the graph. So saying, hey, even though you don't have the equations, can you still write the table and the graph from that? So go ahead and pause it, try and figure out what the table and the graph would be, or the table of the inverse and the graph of the inverse would be, like even though you don't have the equation. Okay, so now that you've done that, as we kind of mentioned earlier, if we just take these and we transpose them, so this -2, -6 would become -6, -2, and then we have 0, -1, 2, 0, 1.5, 1, 0, 2, -1, 3, 0, 4, and 4.55, right? And then if we graph those, we're going to see an inverse there, and I already have the inverse prepared to show you guys. And there's the A original, and then here's the inverse, right? So it should look something kind of like that. This is not the exact E equation, so don't regard those, but it should look that-ish. Okay. All right. So back over here. Let me bring that back over so you don't need that anymore. And okay, so sorry, I missed the question there. Is this invertible? So if we go back to that actual view, on this one, it's not going to be invertible because as we're kind of seeing, our blue line here is not a function because it does not pass that vertical line test. So this is the inverse, but the inverse is not a function. So that doesn't mean that it's not a usable thing or it's bad. It just means, hey, we can only do certain things with it. We like things to be functions because we can do more with them, but that does not mean that a non-function isn't a useful thing for us to have or know about. Okay, on to number 79. So we're kind of past the exploratory phase. We're kind of getting into the actual, hey, let's try and do some of these things out. So I want you guys to go ahead and pause the video, do 79 and 80, and then come back and I will kind of explain through them fairly briefly here. Okay, so on 79, they have the original and then they found the inverse. So first of all, is the equation the inverse of f of x correct? So is this the actual inverse of this? And it ends up being, yeah, that is. But we think that there's a problem, right? If we plug in 1, we get 27 for the A original. So I plug in 1 here, I get 27. So f of 1 is 27. That should mean that the inverse, if I go backwards with it, the inverse of f of 27 should give me 1, but does it, right? So let's try that out, right? I plug in 27 here. 27 divided by 3 is going to give me 9. Square root of 9 is 3. So I get 4 plus or minus 3. So 4 plus 3 ends up being 7, and 4 minus 3 is 1. So I actually get two answers. One of them is 1, and the other one is 7. So is that a problem? Like, what's going on there, right? So the issue is that this inverse is not invertible. Okay, so if it's not invertible, we cannot actually use this notation for it. Okay, that f in the f of x stuff you've been seeing for the past few years, the f stands for function, right? So if I'm going to use this f to the negative 1, which is the inverse of the f function notation, this has to be a function, meaning it has to pass the vertical line test. And this does not pass the vertical line test, right? Because of that plus or minus deal. So there's the problem, right? They did find the inverse, but the inverse is not a function. So that's why we kind of have these problems and kind of why we need to worry about and care about those things. All right. And then down to number 80. So at the right is the graph of this. Copy the graph and you sketch the graph of the inverse. So what we should find is that this vertex is going to move over here to the y-axis at 4, and then it's going to be this horizontal parabola there, right? So what they're trying to get you to see here is now, well, that inverse there is not a function, but what part of it could be, right? Well, this right-hand side of my function here, let me just actually pull this up on Desmos so I can graph it a little bit nicer for us. So let's just do x minus 4 to the second, right? So there's the graph. It might not be the exact same, but close enough for us, right? But then if I graph the inverse of that, which is going to be x equals y minus 4 to the second, right? There's my inverse graph, right? Let's just turn that one off. So the right-hand side of this blue graph, it gives me, from its inverse, when I reflect it, the top half of my green graph, right? And the left-hand side here actually ends up giving me the bottom half of my green graph. So if I need my green graph to be a function, I really just need to get rid of one of those halves. So I can get rid of this bottom half, and boom, I've got myself a function there. So that's kind of the thing they're trying to get you to kind of notice. And well, how can I do that? Well, if I were to get rid of the left-hand side of my blue graph that would also get rid of the bottom part of my green graph, making them both functions, making them invertible, meaning that I can do a whole lot more with these. And that's kind of where this is ultimately trying to get us to go. All right. And then to finalize here, 81 and 82. I don't really need you guys to do every single one of these, but I would like you to try and do one problem from A, B, or C there on number 81. So I'll go through the process, but if you want to try one first. If you're not sure how we can test it, what we're actually doing here is finding the f of g of x, and that should give us x, and the g of f of x, and that should also give us x. If both of those things are true for an equation, then it ends up being an inverse. That's kind of how we test to see, hey, are these two functions inverses of each other? So I'll go ahead and do one of those ones for us. Let's give myself some more room here. So we're going to take a look at, we'll do the second one. We got f of x is rad x plus 2, and g of x is x squared minus 4x plus 4. So if I do the f of g of x, what do I get? So I'm going to take the g and plug it into the f. So that's going to be the square root of x squared minus 4x plus 4, then plus 2. Well, that looks really, really ugly. Well, how can I work with this inner part? Well, I can factor it. Let's see if that helps. It's just going to help, right? Multiply to be 4, add to be negative 4. It's going to be x minus 2 and x minus 2, which is another way of saying, hey, it's the square root of x minus 2 squared plus 2. Well, the square root and the square root are going to cancel out, so I'm just left with x minus 2 plus 2, which is, hey, just x, which is what we should get, right? Awesome. So it's really, really tempting to say, well, it worked there, we're good, it's an inverse, but you need to check the opposite way too. So if I do the g of f of x, what do I get? Well, I'm plugging the f into the g, so that's going to be the square root of x squared minus 4 times, oh, I forgot to put the plus 2. So square root of x plus 2 squared minus 4 times square root of x plus 2 plus 4, right? So let's multiply this out. So this is where it gets a little bit nasty, but it's not too bad. If I FOIL this out, I will get x, and then 2 rad x plus 2 rad x is plus 4 rad x, and then 2 and 2 is 4. And then here, this would be a negative 4 times rad x. Negative 4 times 2 is going to be a negative 8, and then I have the plus 4. So all stuff should cancel out here. My 4 rad x's are going to cancel out. 4, 4, negative 8 are all going to cancel out. Left with just g of f of x being x, which is the other one. So they both end up being x. Now that is how we verify, hey, these are inverses. It's a bit of work. I'm going to have you guys do it more for the practice of working with the compositions of like functions, and then knowing, hey, yeah, it works because I got the x, versus it being a legitimate, quick, easy way to test if things are inverses. It's going to be a lot easier just to graph them and see. But this is the algebraic way that I'm going to have you guys do, again, primarily to have you to check your algebra and your composition of function skills, versus just to see if it's an inverse or not. All right, so with that, the last one here on number 82, write an equation of the inverse of each function below. Use correct notation for your answer. Okay, so I'm going to do part B here for us, because B has a very special clause or case in it. So I want to kind of show you how we deal with that. So on part B, we're going to have, we say the g of x is square root of 2x plus 4. Okay, so if I want to find its inverse, this is basically y, so I can change it to x is equal to square root 2y plus 4. I could square both sides, and I get x squared equals 2y plus 4 minus 4. X squared minus 4 equals 2y. Divide everything by 2, and I get x squared minus 4 over 2 equals y. And that would be my inverse. Okay. Now, if I graph these, there's going to be a problem. So let's take a look at those graphs. So my first one was 2x plus 4. And then my inverse, I said, my inverse was x to the second minus 4 divided by 2. Okay, so graphically we can say, hey, those are inverses because this blue line is missing the bottom part of it, right? So this is actually not the inverse, right? Because my blue was my A original, my green can't be my inverse because it gave me more than my A original did. So what we need to do is what's called restrict the domain here. So if I go back to this, I need to restrict the domain on this part. Now what do I need to restrict the domain to be? Well, if I look at my screen here, I need it to be only the right-hand side of this graph. So that is when x is 0 or bigger, I'm good, but when I'm less than 0, I don't want that anymore. So that's when I'm going to go ahead and take off. So if I go to this, the notation that I would actually say is y is equal to x squared minus 4 over 2. I'll put a little comma there for values of x that are greater than or equal to 0. So that little extra bit there is what's called a domain restriction. And that basically tells us, hey, it's this, but only under this particular region. And you've probably seen those all the time when you've seen like mathematical equations or formulas say, hey, it's this for x is not 0 or x is not -1 or things like that. There are these qualifying statements which we use to say, hey, this works so long as this condition's met. So in this case, it's a domain restriction saying, hey, only use these values and then it works just fine. So I wanted to kind of show you guys that one, mostly to show you how that domain restriction looks. I'm not expecting you to be an expert on the domain restrictions yet. I just wanted to point that out so that you guys can see that and kind of know what's going to be coming, or maybe because we're going to be doing a bit more of that coming up in the future. All right, we're almost done. We're going to wrap it up here. So on your own here, I want you guys to try and answer these questions for yourselves. Just kind of think about how you are thinking and what you know, and then we're going to close it off here. Okay, so homework-wise, we have 84 through 90, so that will be our homework for 1, 2, 2, and with that, I will talk to you guys later.